All right, excuse my appearance. I had chocolate for breakfast. I haven't shaved for a week. It's a pandemic. Still washing. Ooh. TMI Thornley. All right, question 1, sublimation. Sublimation is to do with turning a solid to a gas. It has to be the same chemical. Don't break it apart or make another chemical. It has to be the same chemical. So that looks like 1 is C. No, it's not. 1 is B, idiot. C is gas to solid, which is reverse sublimation. We want B, solid to gas. Question 2. What's the empirical formula the same as the molecular formula? Well, what you've got to do is you've got to add up the mass, the molar mass of the empirical formula and see if it's the same as the molecular formula. Let me do that. So I've got 12 plus 16 plus 16 plus 1. What's that? 45. So if the empirical formula is 45 and the molecular formula is 90, then the actual molecule itself must be CO2H twice. No, so that can't be the right answer. I want the empirical formula to be the molecular formula. I think it might be the last one. Doing it quickly in my head here. It's 4 times 12 plus the 8 there plus 16. 72, yeah. So the empirical formula and the molecular formula is the same. So 2 is D. 3 is uber tedious, which is limiting. Oh, cheeky. I worked it out before. It is B. But let's get there from first principles. All right then. I know that, let's exclude some for a start. I know that sodium hydroxide and nitric acid react in a 1-to-1 ratio. So if there's the same moles of each of them, neither is going to be excess or limiting. So it isn't that one. The same thing applies for this nitric acid, sodium hydroxide, 1-to-1 ratio. I've got twice as much sodium hydroxide as nitric acid. So that means the sodium hydroxide must be in excess. We're looking for limiting. So that takes us to A and B. I'm just going to write out the equation. Sodium hydroxide, sulfuric acid goes to sodium sulfate and water. Balance it. Now let me put the moles underneath. Let's do this one first. 0.2 and 0.1. How do you work out which is limiting? Well, take the moles and divide it by the coefficient. Take the moles and divide it by the coefficient. Whichever of those numbers is lowest, it's limiting. 0.2 over 2, 0.1 over 1. It's the same, isn't it? So this one, there's no excess, there's no limiting. So it isn't A, it is indeed B. It's B, by a process of elimination. 4's the most difficult. 13% of people got this right. So an ideal gas, I like to imagine a gas in a box. The volume of the individual gas particles is 0. Not the volume of the gas in total, just each particle is 0. And if I want to make an ideal gas better, if I want to make the gas more gassy, if I make the gas more liquidy, then I make it worse. So if I increase the temperature of the gas, it's less likely to be a liquid now, isn't it? And if I decrease the pressure of the gas, it's less likely to be a liquid. Conversely, if I cool a gas, it's going to liquefy, and if I increase the pressure, it's going to liquefy. All right then, why do gases deviate from ideal gas? So deviating is this here. This is where you treat the gas so badly, it begins to liquefy. Molecules have finite volume. Well, first of all, let me simulate the high pressure. Let me move the lid of the box all the way down and then put all the gas particles at the bottom here. So I've reduced the volume and I've simulated the high pressure. Now the problem is if you squash the gas particles down into that small place there, they start to liquefy, they start to stick together. And you'll realise as you squash them that they don't actually have zero volume. They actually start to occupy real volume. And so the answer is A. Oh, that's a nasty one. You might be able to get there by excluding the others. Let's have a quick look. Cohesive forces increase the volume from the ideal gas. So B makes no sense. C, increasing pressure increases the temperature of the gas. That's true. If you squash a gas, it gets hotter. But don't forget, hotter's good. If you heat up a gas, it becomes more gassy. What do you mean by more gassy? When the particles collide, they're more likely to bounce off, which is a property of an ideal gas. If the particles collide and they stick, then that means your ideal gas law is going to be broken. You want elastic collisions. And D, so C's wrong, and D, collisions between the molecules occur more frequently. That's true, but that doesn't make any difference. So they collide. As long as they bounce off, that's all good. So you could get there by excluding the others. 5. Oh, this is a bit easier. Now, the IB loves chromium because they normally ask you about the electronic configuration, because it's one of the dodgy ones. With that there. What have we got? So this is the number of protons. It's the atomic number. That's the number of protons plus neutrons. That's the mass number. And together they are called nucleons. All right. Oh. Acoustic issues. So it's C, isn't it? 5C. The difference between the mass number and the atomic number is the number of neutrons. Don't get nucleons, protons and neutrons, confused with neutrons. 5 is C. 6 is a selenium ion. Well, let's go up to the periodic table. Selenium is here, and if it's an ion, it's going to want 2 more electrons, so it has 36 electrons. So the selenium ion is going to have 36 electrons. So that's 36 here. That means it's going to end in 4p6. All right. So which ones end in 4p6? I've got B and I've got C. So that means there must be, B and I've got D. That means there must be a mistake somewhere within the electronic configuration. Yeah, for B, they mentioned 4d10. No, it's 3d10, isn't it? That's wrong. So the answer is 6d. 7. What's a metalloid? Well, metalloid, also known as semi-metal. Oh, Jehubas. So let me draw in the little staircase. No one's quite sure how far it goes because a lot of the elements at the bottom of the staircase haven't really even been experimented on. They've only made a few atoms. Anything above and below the staircase is a semi-metal. With one exception, aluminium is a metal. So they like to ask about that. So what's a metalloid? It looks like arsenic, isn't this arsenic here? Yeah. So arsenic is a metalloid. So we're looking at 7b. Question 8. All right, let's do the easy trends to see if they work. Let's look at atomic radius first. So I think fat Frank, francium's the fat one at the bottom, it's the biggest atom, and everything else gets smaller away from fat Frank. No, A's wrong. The other easy one is electronegativity. You've got the periodic table. Hopefully you know that fluorine has the greatest electronegativity of 4. So as you go this way, it gets bigger, and as you go this way, it gets bigger because fluorine's the highest. If you go down the group, decrease across the period. Yeah, 8D. 8D. Now, that is the best answer, not the correct answer, because the noble gases, their electronegativities don't necessarily fit that pattern. But there we go. It's the best answer. Question 9. Wow, how quick are you at drawing Lewis structures? Hopefully some of these you still remember. Ammonia, well, that's going to be polar. Nitrogen has the highest electronegativity. Boron trifluoride. Boron can have 6 or 8 electrons around the central atom. So that's the answer. That one's non-polar. Why is it non-polar? Why is anything non-polar? The preferred terminology is the bond dipoles cancel. So in this case, the bond dipoles cancel. I've got a bond. Oh, I've got this, and all of those bond dipoles cancel. That's a little big. There we go. So the answer is 9C. Just for completeness, here's the other Lewis structures. Oxygen difluoride's polar, and sulfur dioxide is also polar. It's bent. Right, question 9 done. Question 10. Ionic and covalent bonds. So I'm looking for something plus, something minus, and within one of those, there's going to be some covalent stuff. Normally for the plus, I've got ammonium that has covalent, and for the minus, maybe there's some carbonate, maybe there's some nitrate, some hydroxide, who knows, phosphate. So what have we got? Yeah, B. So B is the answer, because I've got some sodium ions and I've got the carbonate ion. 11. Resonance structures. So resonance structures, they have double and single bonds next to each other. Always. Not always. Between the carbons can be oxygens too, like in ozone. And the most classic resonance structures, the IB likes to have nitrate, carbonate, ozone, benzene. These are the ones that keep coming up. So that gives 11D, because it has the carbonate in it. 11D. 3 resonance structures. 12. I got this one wrong. I got 29 out of 30 on this test the first time round. The internet disagrees with the IB, but the IB syllabus says dipole-dipole, dipole-induced dipole, London dispersion forces are van der Waals forces, which gives B, 12B. All right, they make the rules for now. 13. So for 13, you've got to use this equation. Delta H is minus MC delta T over the moles of fuel. M is the mass of what's heated, so that's going to be 50 grams. The specific heat capacity of what's heated. That's the first of the many tricks in this question coming up here. This is joules. Well, why don't I want kilojoules? Why have I got it in joules? Well, if this is grams, then this must be grams, and this must be joules. Okay. So I have to somehow account for 1,000 a little later on to turn my joules to kilojoules. Temperature change is delta T. And the moles of fuel, just take my word for it. It's tempting to look at both of these, since they both react, but just look at one. So I've got moles is concentration times volume, which is going to be 0.1 times 25 milliliters. Well, convert to decimeters cubed. So I don't know why it isn't accounting for both of those chemicals, or you double your answer. You just choose any one. I'm not entirely sure why. So at the bottom, moles of fuel, which is going to be this number here, 0.1 times 0.025. And I'm going to put my 1,000 in for that kilojoule trick, which answers that. None of them. I'm going to cheat and look, it's D. Why is it D? Okay, they combined this together to make 25. How cheeky is that? So the answer is 13D. All right. 14 looks tricky, but I'm not even going to read the question. It's just numbers going this way equal numbers going that way. So clockwise numbers sum to anti-clockwise numbers in a Hess cycle. So I've got y minus 1301 equals minus 788 minus. Just going to unobscure that number. So solve for y. Y is going to be minus 788 minus 286. And then you're going to move this to the other side, change the sign, plus 1301. That's A. 14A. That's Hess's law. 15, this comes up all the time. You're breaking that silicon-hydrogen bond. What's the energy to break that? Well, first of all, you have to make sure that everything's a gas, because average bond energies only work with gases. So what can I exclude? I can exclude none of them. They're all gases. Okay. Also, when I break the bond, I don't want to make any bonds. So once I've broken it, don't make any more. And so I can exclude C because I'm making hydrogen, H2. That's breaky and makey. We just want a breaky. D is wrong because I've broken all 4 bonds and I have to just break one. So D's wrong. D's actually 4 times too big. I think A and B are functionally the same, but the IB prefers B. So break these 4 bonds, getting a number 4 times too big, and then divide by 4. So 15's B. 16, reactions, collision theory. Reactants have to collide in the correct geometry with energy equal to or greater than activation energy. So that would be I and II, which is A. 16A. Question 17. This causes people a lot of trouble. All right, so let's say the acid runs out first, it's limiting. So if I have half the concentration of acid, and that was going to run out first anyway, then I'd get a line that ends lower. So this is if I have half the concentration of acid. And so that is going to be B and D. It's a line that would end at half distance. So B and D only goes halfway, so it can't be B or D. So I'm left with using larger or smaller lumps of chalk. Well, the gradient of this line here is a little steeper, so it's going a little faster, and it finishes a little earlier. So what's going to go faster? Is it going to be the lumps or the powder? It's going to be the smaller lumps, isn't it? So it's C, 17C. 17C. 18. I got some equilibrium. What is that? Oh, is this banging? Oh, that must be annoying. I've got chlorine nitrite, nitrogen monoxide goes to some funky thing plus NO2, and that's going to be delta H is negative. Okay, equilibrium. If I increase the temperature, well, the only thing that changes Kc is temperature. So that means B and C must be wrong because Kc changes. How do I know Kc changes? Because temperature changes. Le Chatelier's principle states that for a system in equilibrium, if you stress it, it moves to oppose the stress. So I'm heating this equilibrium up, and it's going to move to oppose it by cooling it down. Now, since this is exothermic, that's plus hot, I think, and that's plus cold. It's endothermic, the other side. So if I heat it, it's going to favour the reverse reaction until equilibrium is re-established. It's going to favour that, the reverse reaction, and this equilibrium is going to shift to the left. So that means it has to be A, because that's the only one remaining. It has to be A. 18A. Just quickly for Kc, just to confirm, so Kc is the concentration of products over reactants. And I'm going to have more reactants if the equilibrium shifts to the left. 19. Bronsted-Lowry acid-base pair are different by H+. So I just got to look for a pair that's different by H+, that's C. That was easy, 19C. 20. Gases that do not result in acid deposition. Oh, that's a bit saucy. So carbon dioxide makes carbonic acid. So it's not that. NO2, well, if I add that to H2O, then I'm going to get HNO3, that's nitric acid, so it's not that one. Nitrogen monoxide, I'm not sure about, so we'll wait on that. But sulfur dioxide, yes, sulfur dioxide, if you add it to water, makes sulfurous acid. Not sulfuric, sulfurous acid. So it's this one here, it's C, 20C. Beep, 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 beep. Back it up. The IB says 20's A. Does not result in acid deposition. Let me check the examiner's report. 20. Oh, saucy, saucy, saucy. So they direct you to the syllabus, fair enough. Acid deposition means that you have a pH of less than 5, and natural carbon dioxide in natural beautiful rainwater is pH 5.6. Oh man, that's 2 I got wrong. That's terrible. Okay, we're still learning here. 21 is manganese for oxide. That's the question. So 21 is D. How do we get that? So MnO2. The sum of the oxidation states is the charge, which is 0 in this case, the overall charge. Oxygen in the compound's -2, which leaves manganese to be +4. And 4 is IV in Roman numerals, 21D. 22. Voltaic and not electrolytic. So a voltaic cell is the one with the voltmeter and the salt bridge. And the electrolytic cell is where you do electrolysis. That's where you zap something. You break it apart into its elements in in SL. An electrolyte is required. So, yeah, an electrolyte is required for both of them because an electrolyte is a liquid or solution that allows the passage of electricity and is also changed by it. Well, that's the whole point. So, that one's correct for both of them. An anode is where oxidation occurs. Well, I just think red cat. Reduction always happens at the cathode, so oxidation always happens at the anode. Oh, that's true for both of them, so that's the wrong answer. C, ions move in the electrolyte. Yep, positive ions move towards the negative electrode. Negative ions move towards the positive electrode, so it must be D. Electrons flow from negative electrode to the positive electrode. Oh, yeah, that's a hard thing to prove from first principles, but you can exclude the others. 22 is D. 23. How many alcohols have that formula? Well, I've got a butanol, so butanol. Ooh, that's not butanol, is it? 1, 2, 3, 4. This is butanol, butanol. Then I've got butan-2-ol. Then I've got this funky thing, 2-methyl-propan-1-ol. Is this another one, or is this the same? That's the same. Any more? Any more? Butan-3-ol is butan-2-ol, butan-4-ol, butan-1-ol. Yes, aha. I knew there was a trick, I just had to find it. You can pop the alcohol on there, 2-methyl-propan-2-ol. There's 4. 23 is B. Oh, okay. Back on track, Thornley. 24. The alkynes. Let's draw it out from like this. So I've got ethyne, C2H2, which is C3H4. Every carbon's got to have 4 bonds. Let's try one more. C4H6. So that looks like CnH2n minus 2. Yep. CnH2n minus 2. 24B. The other ones you expect to know, alkanes, CnH2n plus 2. Alkenes, CnH2n. 25. What compound can be esterified and turned solution green? So if I want to make an ester, I'm going to need an alcohol and a carboxylic acid. But only one of those will turn potassium dichromate 6 green, and that's the alcohol. And it pretty much has to be, therefore, a primary alcohol or a secondary alcohol. Tertiary alcohols don't react with it. So which one's the primary alcohol? The primary alcohol is, I think it's C. Let's have a look. C. I've got CH3, CH3, H. It's a secondary alcohol, but that still counts because primary or secondary will work. So that's going to be 25C. Tricky. 26. Ethane and chlorine. That's initiation, propagation, termination. Everyone seems to understand it, but no one seems to be able to answer the questions on it because they think, we haven't done this. Yes, we have. It's initiation, propagation, termination. So that's going to be free radical substitution. Yeah, 26A. Don't forget the chlorine is broken apart by the ultraviolet light. And then you swap a chlorine out for the hydrogen 1 by 1 by 1. So 26 is A. 27. Oh, that's a long question. So you're reading from the top of the meniscus. Well, that's wrong. That's going to be a systematic error. Actually, let me draw the top of the meniscus in correctly. That was the meniscus for mercury, my mistake. So you're supposed to read from the bottom of the meniscus. If you read from the top of the meniscus, your value for the volume is always going to be too high. You think you think that you've got 10 millilitres, but really you've only got 9.9 millilitres. You're reading the volume too high consistently. So that's a systematic error. Systematic error. So it could be A or D. A or D. And I'm thinking it's going to be A, because it's pretty accurate. You did the same thing each time. So your values are going to be, no, it's not. Accurate is your number has to be close to the accepted value. So it's inaccurate, isn't it? It's inaccurate. Your number won't be close to the accepted value. Or is it close? Because what's the difference? Just a couple of drops? I don't know. 27D. 27D. Oh. So accuracy refers to how close your value is to the expected value. I would say this is probably a poor question, because you're going to be really close if you're reading it from the wrong side of the meniscus. 28. What's the relationship between these variables? Missed, idiot. Alrighty, so if I've got y and x, so I've got -1, 1, -2, 2, -3, 3. What the hell's going on there? Isn't it C? Y is proportional to -x. 28C. Yeah, strange question. 29. H1 NMR. Well, H1 NMR can only measure hydrogens in your molecule. It can tell you the hydrogen environments and the number of hydrogens in those hydrogen environments. Well, the ratio of those hydrogens in those hydrogen environments. Is it just hydrogen? The number of hydrogen environments. Yes, so that's correct. Let's check the others. Total mass of hydrogen. No, that maybe would be a mass spectrometer, maybe. Vibration frequency. No, that's infrared. Ionization energy. Oh, that's some kind of line spectra business there. So it's 29 is A. And 30. Oh, man. It's dark outside. It's bad enough. Index of hydrogen deficiency. Okay, so for every ring, you have 1. For every carbon-carbon double bond, you have 1. For every carbon-carbon triple bond, you have 2. So let's just have a look. What has an index of hydrogen deficiency of 1? So it's either got 1 carbon-carbon double bond or it's got a ring. I see. So the first one is benzene. That's got an index of hydrogen deficiency of 4, 1 for the ring and 3 for each of the 3 double bonds. So it's not that one. C2Cl2 has a double bond, triple bond, excuse me. So that has an index of hydrogen deficiency of 2. So it's not that one. C4H9N. I'm going to give that one a drop. It might be that one, but there's so many different isomers. I'm not sure what they're talking about. C2H6O. So, oh, that's gone a bit small. C2H6O. Isn't that just ethanol? Or ether? So I think it has to be the weird one. 30 is C. 30 is C by a process of exclusion. I think we're done. Good night.